Okay, let's kick things off. The future of energy. It's a massive puzzle, isn't it?
It really is, especially with climate change pushing us. How much energy would we actually need as we, transition?
Exactly. And figuring that out is crucial. So today we're diving deep into a specific study called Energy Demand Estimation using a pre-processing macroeconomic modeling tool for 21st century transition analyses. Quite a mouthful.
Huh, yeah. But it's fascinating because this study tackles that very challenge head on, forecasting energy needs during this huge shift.
And it's critical, right? If we guess wrong on future demand, well, building a sustainable energy system gets a whole lot harder.
Definitely misses the mark. So this study, it's looking way ahead, predicting global energy demand right out to 2100.
And they've developed a new tool to do it called LUT demand.
That's right, LUT demand. It's their attempt to bring maybe a bit more detail, more transparency than some of the existing models perhaps offer.
Okay. So, our mission for this deep dive seems pretty clear then. We want to understand the key things driving future energy demand and what that means for this energy transition everyone's talking about. All based on this study, energy demand estimation using a pre-processing macroeconomic modeling tool for 21st century transition analyses.
Precisely. And this study really highlights, look, getting this demand forecast right is absolutely crucial, especially for hitting those Paris Agreement goals.
Makes sense. If you don't know the target, how do you aim? How do you plan the renewables, the grids, everything?
Exactly. And the study suggests that, well, some of the current methods, the ways we model demand, they have some limitations.
Like what sort of limitations are we talking about?
Well, this study argues they might lack enough detail or transparency, or maybe they don't fully explore how different big picture economic scenarios could impact things.
Uh-huh.
Think about the big players like the IPCC using their integrated assessment models and SSPs.
The shared socioeconomic pathways?
Yeah, those. Or the IEA's World Energy Outlook. Super important work, obviously, but this study suggests there can sometimes be maybe issues with data availability or just how clear the methods are.
Okay, so this is where LUT demand, the tool from the study, steps in, trying to fill those gaps.
That seems to be the goal, yes. They introduce it as a novel approach, and the authors stress it's designed to be comprehensive but also, user-friendly.
And open access, you mentioned?
Critically, yes. Open access, the repository link is out there. We can mention it again later maybe so anyone can actually use it, test it, build on it.
That's huge for transparency. So what exactly were the researchers trying to do with this tool in this specific study?
Well, the main goal, they state, is to really assess and discuss how these different macroeconomic futures affect final energy demand, the FFE.
Okay.
They do that by modeling the underlying need, first the energy service demand, ESD, and then they look at the knock-on effect on total primary energy demand, TPED, way out to 2100.
Oh, okay. So ESD to Fed to TPED.
Right. And the authors felt that this kind of end-to-end assessment, especially looking out to 2100 in the context of 100% renewables, was kind of missing in the existing literature. That's a key motivation here.
And this study also looks at carbon removal, pulling CO2 from the air, negative emissions.
Yes, exactly. They specifically investigate how needing negative emissions might impact that total primary energy demand figure, which is, increasingly relevant.
Definitely. Okay, so LUT demand sounds quite ambitious according to this study. What makes it stand out? What are the novelties they're claiming?
They highlight a few key things. First, it's got high resolution spatially, so country level, and temporally, looking in 5-year steps to 2100. Second, it covers a really broad range of sectors: power, heat, transport, all modes industry, even desalination and carbon dioxide removal, CDR.
Wow, that's comprehensive.
And third, they include power to X, using renewable power to make things like hydrogen fuels or chemicals. The authors argue these elements make their approach pretty innovative.
That is a lot of detail. So how does it actually work? How does LUT demand get from, say, an economic forecast to an energy demand number in this study?
Well, they lay out this 3-level approach. It starts with the basic need, energy service demand, ESD, wanting a warm room, needing to travel, that sort of thing.
Right, the fundamental service.
Then it calculates the final energy demand, FAD. That's the actual electricity or heat or fuel you consume at the endpoint to get that service.
Like the petrol in the car or the electricity for the heat pump.
Exactly. And finally, it estimates the total primary energy demand, TPED. That's all the raw energy needed before conversion, mining the coal, generating the power, processing the fuel. It accounts for system efficiencies.
Got it. ESD-EV-TPED. Makes sense. So what kind of futures did they feed into this model? What scenarios did the study explore?
They looked at quite a mix. They used the established shared socioeconomic pathways, the SSPs.
Which give different storylines for how the world might develop socially and economically.
Right. But they also created three new scenarios themselves called the LUT scenarios, named after their university. These are a big part of their analysis in this study.
New LUT scenarios, what's the main difference between those?
The key distinction is about when they assume the world reaches economic equality, meaning every country has the same GDP per capita.
Ah, okay. Interesting angle.
So LUTDs assumes this happens relatively early, by 2100. LUTDs pushes it out to 2175. And LUTDs assumes it takes much longer, maybe 2300.
And they specified this doesn't account for inequality within countries, right?
That's an important caveat they mentioned in the study. Just focuses on the national average GDP per capita.
Okay. And how do these LUT scenarios stack up against the SSPs that they also used for comparison in the study?
Well, they included SSP GDP data from both IASA and the OECD. The SSPs have those distinct narratives, SSP 1 and 2 with more moderate growth,
And SSP 3 and 4 with less growth.
and SSP 5 with really high growth. So using these provides a useful benchmark for the results from their own LUT scenarios in the study.
So a broad range of economic futures. Did the pattern of growth differ between the LUT and SSP scenarios in the study?
Yes, quite significantly.
Yeah.
The LUT scenarios tend to show strong growth earlier on, but then it sort of saturates, flattens out towards 2100.
Okay, leveling off.
Whereas some SSPs, especially SSP 5, project more continuous, maybe even accelerating growth for much longer. This difference in trajectory is something the study explores.
Got it. And population obviously is a huge driver too. What population forecasts did this study use?
They used several. The standard UN low, medium, and high variants were included. Plus, they used the population projections that go along with each of the 5 main SSP scenarios. So altogether, 8 different population pathways were plugged into LUT demand for this research.
8. Wow. So what's the range we're looking at by 2100 across those scenarios, according to the study?
It varies a lot. Some scenarios, like SSP1, SSP5, and the UN low one, actually see global population peaking mid-century and then declining to maybe 7 or 7.5 billion by 2100.
Okay.
Others, like SSP2, 4, and the UN medium, land somewhere in the middle of maybe 9 to 10.5 billion. And then you have the higher end, SSP3, and the UN high variant, projecting continued growth up to maybe 12.5 or even 15.5 billion people by century's end. This range is pretty critical context for the energy demand numbers in the study.
Definitely sets the stage. Okay, so we have the scenarios. Let's get back into the model itself, LUT demand. How does it estimate that first-level energy service demand?
Right, the ESD. This study emphasizes it's the foundation, the underlying need for heating, lighting, transport, etc. The study uses what they call a trendline approximation. Basically, it looks at historical data linking ESD per person to GDP per person.
So as economies grow, demand for services tends to rise, and they model that trend.
That's the core idea in this part of the study's modeling. They use historical data for different services and fit trend lines. For heating, it might be linked more to temperature data, but mostly it's GDP per capita. They use statistical tools in MATLAB to find the best fit curves from the data.
Okay. And which specific sectors did they model this for? You said it was comprehensive.
Yeah, the list in the study is pretty long. Power for lighting, appliances, heat for space and water, transport, road, rail, marine, aviation, passenger and freight.
Okay.
Industry. Cement, steel, chemicals, aluminum, pulp, and paper, plus desalination, waste management, and even that carbon dioxide removal, CDR. The authors highlight this wide coverage as a strength.
That is incredibly detailed. So once they have that ESD, the need, how does this study get to the final energy demand, the FD?
So the step from ESD to FD, as the study explains, is where you figure out the actual energy consumed by the end user.
Electricity, the fuel.
Exactly. Electricity, heat at specific temperatures, like low, medium, high fuels for transport, even raw materials like chemical feedstocks. This conversion step specifies the type of energy needed.
So it's not just how much service, but what energy delivers it, according to this study.
Precisely. It involves translating, say, passenger kilometers into the gasoline or electricity needed, considering whether it's fossil fuels or maybe e-fuels. And it links industrial output, like tons of steel or desalinated water volume, to the specific energy inputs required. This detailed breakdown is key to the LUT demand model presented in this study.
And the study mentioned flexibility in defining how things like EVs or e-fuels get adopted. How does LUT demand handle that?
Yeah, as described in the study, the tool lets users define those transition pathways. So you can set assumptions about how quickly EVs take over or how fast e-fuel production ramps up.
Okay, so you can explore different speeds of transition.
Exactly. Which is crucial for exploring different what-if scenarios about the energy transition itself, a core aim of this research.
Okay, ESD to Fed covered. Now, the final level in this study. Total primary energy demand, TPED. How's that estimated?
So the authors are clear in the study. LOT demand isn't meant to be a full, complex energy system simulation tool.
Right, it's more focused on the demand side.
Exactly. But it does provide a way to get a quick assessment of how these different demand scenarios impact the total raw energy needed, the TPED. Does this without a full model run.
So things like costs, grid infrastructure, fuel trading, those are outside its scope.
Correct. The study notes those are limitations. The TPED calculation gives you the total primary input needed, accounting for upstream energy use and conversion efficiencies.
So how does it actually calculate that TPD number in the study?
Well, the approach described involves setting up a baseline of the 2020 energy system, which they checked against IEA data. Then they define future shares for different primary energy sources, like renewables, nuclear, fossil fuels,
Okay.
and set a timeline for the transition between them. They also align the implied CO2 emissions with other climate studies. But the key thing, the study says, is that TPE really depends on that initial macroeconomic scenario and how efficiently we convert primary energy into useful final energy.
Okay, that framework makes sense. So we've got the problem, the tool, the scenarios, the method. Now the results. What were the key findings of energy demand estimation using a pre-processing macroeconomic modeling tool for 21st century transition analyses?
Well, the study really hammers home the significant impact of those macroeconomic scenarios, starting with ESD, energy service demand.
Okay.
For electricity, for example, the projections varied hugely by region and by scenario. Some high-growth scenarios saw electricity demand potentially saturating later in the century.
Leveling off again.
Yeah, while lower-growth ones often still showed demand climbing. Heat demand was interesting, too, with industrial heat linked to GDP and population being a major driver, according to the study.
And how did that translate into final energy demand, FAD, in the study's results?
Well, the macroeconomic scenarios really shaped the total FAD trajectory. Interestingly, the study found that faster GDP growth could sometimes mean a less pronounced dip in FA around mid-century,
Wait, faster growth means less of a dip? How does that work?
because the rapid economic growth drives up the underlying energy service demand so fast they can actually outweigh the gains from energy efficiency improvements during that period. That's what the study suggests.
Okay. The demand growth outpaces the efficiency gains.
Right. And the study also noted that even with a big shift to renewables by 2050, we could still see significant additional FAD growth in the second half of the century. Things like developing economies catching up, continued population growth in some scenarios.
So the transition doesn't necessarily mean overall demand stops growing post-2050. What about the mix of that final energy? Did the composition of FAD change much across scenarios in the study?
Oh, absolutely. The mix was quite sensitive, the study shows. Electricity demand, for instance, seemed more responsive to the very high-growth SSP5 scenario compared to the high-growth, then saturating LUTEs scenario.
Interesting. Why?
Well, the study suggests maybe part of it is that a big chunk of heat demand is for space heating, which their model doesn't directly tie to GDP. They also noted CDR becoming a bigger factor in heat demand later on.
Right.
But things like transport fuels and industrial feedstocks, very strongly linked to the macroeconomic assumptions. That's a key finding highlighted in this study.
Okay, so the economic future really dictates the what and how much of energy use. Let's go to the top level then. Total primary energy demand, TPZD. What kind of range did this study find for 2100?
The range was pretty wide, as the study reports. The highest estimate came from that LUTEs scenario, the one with early global economic equality reaching around 399 petawatt-hours, PWH.
Wow, 399 TWH, and the lowest.
The lowest was the SSP1 scenario, the sustainability pathway, projecting about 222 pWh.
Goodness, that's nearly a twofold difference. That really shows you, the listener, just how much uncertainty there is depending on these big societal
It
choices.
really does. And the study noted that many of those high-demand scenarios like the LUT-1s and SSP-5 actually showed TPED starting to saturate by 2100.
Leveling off again.
But the lower demand scenarios often showed TPD still increasing towards the end of the century. SSP1 was kind of the exception there, showing a decrease. These numbers are really central findings of the study.
That's a huge spread. What role did renewable electricity play in these TPED projections in the study? Did it help keep the numbers down?
Well, the study emphasizes that, yes, the big shift to renewable electricity does have the potential to limit overall TPED growth because, converting primary sun or wind to electricity is often more efficient than burning fuel.
Right.
But they also stress that strong economic and population growth can still drive significant increases in TPED, even with lots of renewables.
So renewables help, but they might not be enough to counteract really strong demand growth.
That seems to be the message. And the adoption rate of e-fuels also plays a big role, as the study discusses. Producing e-fuels tends to be less energy efficient overall, so relying heavily on them pushes TPED up.
Makes sense. Now, what about the negative emissions, the CDR? How did needing more or less carbon removal affect the total primary energy demand in this study?
So this study looked at two climate targets, basically 1.5 degrees Celsius and a stricter 1.0 degree target based on IPCC data. They estimated how much CDR would be needed for each. And interestingly, they found that even going for the much higher CDR amounts needed for the 1.0 degree target only caused a relatively small increase in the overall TPE compared to the baseline demand.
Oh, really? That's actually quite reassuring, isn't it? That pursuing more ambitious carbon removal might not totally blow the energy budget, according to this research.
Yeah, it suggests the energy penalty from more CDR might not be as daunting as the underlying demand growth itself, at least in their modeling framework.
What about the real-world implications? Land use, for instance. Did the study estimate how much land might be needed for all the solar panels and wind turbines?
It did, yeah. It gave estimates for potential solar PV capacity. Yeah. Under that high-demand LUTEs scenario, it could be up to 200 terawatt peak TWP by 2100, which is a lot.
100 TWP, that sounds enormous.
It is. And they looked at wind, too.
Yeah.
This study points out this could create real land use challenges, especially in places like South Asia, which are densely populated and might have high energy demand relative to their land area.
Right. Hearing about that potential scale, especially in crowded regions, really makes you think about the practical hurdles and trade-offs involved.
Absolutely. Renewables solve the emissions problem, but the sheer scale needed, as highlighted by this study, could bring other challenges.
Okay. Let's shift to some of the discussion points the study raised. I remember something about limits to economic growth.
That's right. The study authors note that their own LUP scenarios kind of bake in the idea of economic growth limits eventually. Growth saturates, which, connects back to those older limits to growth ideas from the 70s. They contrast this with some SSP scenarios, which assume growth could potentially continue indefinitely, though maybe population growth slows in those.
And the study mentioned that population density and land issue again in the discussion.
Yes, they reiterated it. In densely populated regions with limited land, finding space for all the needed renewable infrastructure could be a major bottleneck. It needs careful planning.
The study also pushed for looking beyond 2050 in energy modeling. Why did they feel that was so important?
Well, the authors argue that too many studies focus just on the period up to 2050.
Right, that's a common target year.
But the results show huge potential changes in economy, population, and energy demand after 2050. So, to really understand the long-term picture, the ultimate constraints, they argue we need models and optimization that look much further out, towards 2100 and maybe even beyond.
That makes sense. Now, it sounds like this study's overall TPED results were often higher than some other studies, but maybe lower than the really high-growth, high-emission SSP5 scenario. How did they explain that?
Yeah, they acknowledge in the study that comparing results across different studies is tricky because the assumptions vary so much.
Sure. Apples and oranges sometimes.
Right. They suggest their results might be higher than some because their demand modeling is very comprehensive, but lower than, say, SSP5 because they assume a pretty ambitious transition to renewables, which improves overall system efficiency compared to a fossil-heavy future.
Okay. And what about those huge solar PV numbers? How did their capacity estimates compare to other research this study looked at?
The study notes that for the lower demand scenarios, their solar PV estimates were pretty much in line with other research.
Okay.
But for those high demand scenarios like LUTEs, their projections for solar capacity by 2100 we're definitely towards the higher end of what other studies have estimated.
Right. And CDR, carbon dioxide removal, it's controversial sometimes. People debate whether it's a genuine climate solution or an excuse to keep using fossil fuels. Did this study weigh in on that?
They touched on it. The authors suggest that given the strong energy demand growth seen in most of their scenarios, relying on CDR simply to extend the life of fossil fuels could be really problematic.
Because the demand is just too high anyway.
Potentially, yeah. They stress sustainable biomass use is important. And they highlight their default CDR choice in the model direct air capture with carbon storage, DACCS.
Why?
They see it as potentially scalable without the major land use conflicts you might get with, say, large-scale bioenergy with carbon capture, BECCS, though they acknowledge other CDR options exist.
It sounds like LUT demand, despite its strength, still has some limitations the researchers acknowledged in the study.
Oh yes, they're quite upfront about that in the study. They mention some factors like the specific energy intensity of different vehicle types or industrial processes are currently kind of hard-coded. Not easy for a user to change right now.
Okay, less flexible in some areas.
Right. And the results depend on the specific default transition pathway they assumed for shifting away from fossil fuels. Plus, as we mentioned, it doesn't currently include costs or international fuel trade.
But they have plans to improve it.
Yes, they mentioned plans for future development to address some of these limitations.
Okay, so let's wrap this up. What's the big takeaway message from our deep dive into energy demand estimation using a pre-processing macroeconomic modeling tool for 21st century transition analyses?
I think the absolute core conclusion from this study is just how profoundly our assumptions about the future, about economic growth, about population shape our estimates of energy demand.
Right, it's not just a technical calculation.
No. This research, using their LUT demand tool, really demonstrates that these fundamental macroeconomic scenarios ripple all the way through, dramatically altering projections for energy services, final energy use, and total primary energy needed right out to 2100.
It really drives home how vital it is to consider a wide range of possible futures when we're planning something as massive as the global energy transition. This study makes that crystal clear.
Absolutely. Energy demand estimation using a pre-processing macroeconomic modeling tool for 21st century transition analyses and the tool itself offer really valuable insights and a framework for grappling with these huge uncertainties.
So for you, the listener, maybe the final thought is this. As we aim for that sustainable energy future, how do we realistically balance our hopes for economic development and population trends against the sheer fiscal scale of renewables and maybe carbon removal that different pathways might demand? It's a really complex balancing act, isn't it? And this study, Energy Demand Estimation using a pre-processing macroeconomic modeling tool for 21st century transition analyses, certainly paints a clearer picture of the forces involved.
It really does raise those big questions about the future we want and the trade-offs we're willing to make. If you're interested, exploring that open access tool they developed, the link is https://doi.org 10.5281 Could be a really interesting way to engage with the issues this study raises.
Definitely worth checking out if you want to dig even deeper. Thanks for joining us for this deep dive. We'll catch you on the next one.